Here's a great question regarding properties of exponents. How do we rewrite expressions that contain exponents or perhaps radicals, things like square roots, cube roots, etc.? So let's look first at how exponents and roots interact with each other. They're inverse operations, so we can think of them as undoing each other, kind of like you walk down the block and then you walk back, you're back at home, just where you started. So just like addition and subtraction undo each other, the same is for multiplication and division. So check out these two examples. If I take x, I add 5 and then subtract 5, well, I just get back to that plain old x that I started the sentence with. Multiplication and division, some of you might have thought of this idea of canceling, right? Because I've multiplied by 5 and I've divided by 5, simplifies to x. So let's consider a radical expression. So here I'm seeing a cube root and I'm seeing some stuff under the radical. And so I'm going to rewrite the things under the radical thinking about that cubing idea. So I'm going to rewrite 16. And on the side, I'll think about 16 a little bit. So I see 16 splitting into 4 and 4, and then 2 and 2, 2 and 2. So I can rewrite 16 as 2 to the 4th power. So a little bit tricky here, what I'm going to do is I'm going to write the cube root of 16 cubed. I'm going to write it as the cube root as 2 cubed times 2. So in total I have 2 to the 4th. And then I'm going to split up that x to the 4th, and I'm going to say x cubed times x. So I still have the same quantity under the radical. And now I'm going to break up that radical a little further. I'm going to split up, I'm seeing multiplication in there, so I'm going to split up each factor. The cube root of 2 cubed times the cube root of 2 times the cube root of x cubed times the cube root of x. And so now we can see that the undoing is happening. There is a cube here that then gets cube rooted, so those undo each other. There's a cube here that gets cube rooted, they undo each other, but those other two factors don't have an undoing sort of situation, so they'll stay as they are. So let's simplify. I have 2 times the cube root of 2 times x times the cube root of x. I'm just going to rearrange to simplify as my final answer. So I have 2x times the cube root of 2x. So let's look at some general rules here that go with our radicals and exponents. So in general, when there's an exponent on a product, so something like, I'm going to use shapes here as placeholders. Let's say we have a box times a triangle, and there's an exponent on that, like n. I can rewrite that as the box to the nth power times the triangle to the nth power. What about when there's an exponent layered on top of an exponent? Something like a box to the nth power and then raised again to the m power? I can simplify that by multiplying those two exponents together. What about in cases where we have the same base and different exponents? So for instance, multiplication. Let's say I have a triangle to the nth power, and I'm multiplying that by a triangle to the m power. Notice the bases are the same, so I can actually add those exponents. What about in the case of division with the same bases? So here I have a triangle to the n divided by a triangle to the m. You might be thinking, well, if I added for multiplication, you're right, we can subtract for division. So the triangle raised to the n minus m power. What about cases of a negative exponent? So these two final ones are just kind of odd exponents. With a negative exponent, so like box to the negative n, that negative is telling us take the reciprocal of the base. So that can be rewritten as 1 over that base to the n power. And finally, what about a fractional exponent? So that box, again, as our base, raised to the n divided by m. So quite a complex exponent there. Well, that can be rewritten thinking about radicals. So the denominator is the root. Roots are always in the bottoms of things, right? Trees, plants, flowers, that kind of stuff. So we have the box raised to the n power, and then we're going to take a root, and specifically it is the m root. We could also rewrite this as in the other order, so taking the root first, and then raising this whole expression to the n power. So either one of those are great. Let's look at an example. So this example, I have a giant fraction raised to the 4th power. So let's start using our rules to rewrite this. The first thing I'm going to look at is taking this power of 4 and bringing it into the numerator and the denominator based on that rule we just talked about. So here I go. I'm going to say 3 square roots of x to the 4th divided by x y to the 4th all to the 4th. So I've applied one of my rules so far. Now I'm seeing multiplication in the numerator here, and I'm seeing multiplication in the denominator here. So remember, I can take that exponent and put it on each part of those factors. So I'll rewrite 3 to the 4th times the square root of x to the 4th all over x to the 4th times y to the 4th. Oh, and this one I'm going to use parentheses because I have a power on a power. So a couple places to simplify here. I have a power on a number, so I can do that multiplication. I also have a power on a root, so let's do some thinking on the side here. I'm thinking about 3 to the 4th. I want to figure that out. So that's the same as 3 times 3 times 3 times 3, right? Let's do that multiplication. 3 times 3 is 9, and then 9 again, so that simplifies to 81. Okay, so there's one of my little thought bubbles over here. And then let's also think about that square root of x. So the square root of x raised to the 4th, I could think about that as x to the 1/2 all raised to the 4th. And then I'm going to multiply those exponents together because it's a power on a power. So I have x to the 4/2, which hopefully you're seeing simplifies to x squared. So there's how I'm dealing with those two interesting pieces of the numerator. Let's rewrite. So 81 times x squared all over x to the 4th times y to the, let's go ahead and do that multiplication. 4 times 4, right, is 16. Do you see some simplifying we can do here? So I'm going to come over on the other side here and keep going. It looks like I have an x and an x in the numerator and in the denominator. Remember, when we have the same base, we can use subtraction to simplify there. So I have 81, and I'm going to actually visualize it a little differently. So x times x instead of writing x squared. And I'm going to rearrange the order here. So y to the 16th times x times x times x times x. Notice that I have some canceling I can do because I have this common factor of an x, common factor of another x. So all the x's went away in the numerator. They're secretly just dividing out and leaving 1. And then in the denominator, I only have 2 of those x's left. So I'll rewrite using exponents. 81 over y to the 16th times x squared. So this whole mess of fraction and exponents actually simplifies down to this pretty neat and tidy fraction. Let's look at this example again, but do it differently because I want to apply a couple different properties that we talked about that apply to exponents and roots. So this time I'm going to use negative exponents more because I think it might be helpful to rewrite everything in a single line instead of in fraction form. So let me rewrite, not sending in that power of 4 or anything yet, but just rewriting. So I have 3 square roots of x, and then I'm thinking about that denominator, which is xy to the fourth, but because it's in the denominator, I'm going to put a negative 1 on it. And then this whole thing is to the fourth power. So now what I'm going to do is send out that fourth power into all of these factors because I'm seeing multiplication everywhere. So I have 3 to the fourth, square root of x to the fourth, and then I have this denominator that's still in parentheses, so x, y to the fourth, to the negative 1, and oh goodness, to the fourth. So I have layers upon layers there of exponents. Let's focus on cleaning that up a little bit. So I'll just rewrite the first part. And in the second chunk here, this more complicated chunk, let's focus on these exponents. So notice the parentheses here. The 4 and the negative 1 are both on everything inside. So I'm gonna multiply those together. Xy to the fourth to the negative fourth. And now I'm going to focus on bringing that negative 4 into both parts of that product. So here I have part 1 of the product, part 2 of the product, two different factors. So 3 to the fourth times the square root of x to the fourth times x to the negative 4 times y to the fourth to the negative fourth. Let's clean up a little further. We already did some of this arithmetic and figured out how to simplify these guys. So 3 to the fourth was 81. And then square root of x to the fourth, we simplified before as x squared. And then let me leave x to the negative fourth as it is. And I'm going to multiply these powers here on the y because it's a power on a power. So y to the negative 16th. Now, very often in math, we don't like to answer a simplified answer with negative exponents. So I'm going to clean this up a little bit. Negative exponents mean that I should put those things in the denominator. So I'm going to do that. X to the fourth times y to the 16th. Is it starting to look familiar? Now I'm going to simplify. So I'm seeing an x squared in the numerator and an x to the fourth in the denominator. The bigger power's on the bottom. So when I subtract and notice there's a difference of 2, I should have that x squared showing up in the denominator. So I have 81 x squared times y to the 16th. That looks just like our previous example, doesn't it? Same answer, different method. Very cool. So the last thing I want to talk about is when are we going to see this skill in other places in math? We're going to definitely see it when we're simplifying rational expressions, working with scientific notation, maybe solving exponential and even logarithmic equations, working with compound interest at set intervals, so that big old messy compound interest formula you might be familiar with, maybe understanding asymptotes and wholes, and absolutely, as always, at parties with fellow mathematicians.